Remember that the standard matrix for a transformation is the matrix A that defines the transformation T. Back in 7.1, we had a participation activity, 7.1.5, about finding the standard matrix for a transformation that mapped R2 onto R3. They, in fact, gave us the transformation. They said T of X was equal to this matrix, or this vector, right? We're just going from in this case, we were going from R2 to R3. Let me make a note of that up here. This transformation T is going from R2 into R3. And so we know without being told that this is a two-dimensional vector, that there are two components in this vector, but we can also see that there are two different things I can put in or plug in, right, in each row of the result. And the result is a 3x1 matrix, and that's confirmed from here. So what does the input vector actually look like? It's got two components. We'll call it x1, x2. And we kind of have to anyway, because the way the transformation is described over here, you can see that the variables are x1 and x2. I forgot my plus sign here. That's going to take x1 and x2, and it's going to do these things to it, right? It's going to multiply by 4, x1 by 4, and x2 by 6, and add those together, x1 by 2, x2 by -7, x1 by 3, -3, x2 by 5, and add those together, right? And the product, or the result, will be a 3x1 matrix. And we can write this right-hand side here as a matrix equation. We can say that that is 4, 6, 2, -7, -3, 5 times the vector x1, x2. Because I'm going to be doing matrix multiplication, I'm basically undoing matrix multiplication here, but I'm multiplying this row by this column. So each row has to have two components in it. And in this case, I have 3 rows. So each of the 3 rows has 2 components. When I do this multiplication, I get this sequence of sums of scaled components. Okay, but go back up to here, and what I've got is T, I'm not sure what I want to highlight here. T, the transformation of the vector x is equal to a matrix times the vector x. And so what I'm really looking for here is this matrix, right? And what that matrix is here is this 3x2 matrix down here. This is equal to the line above. And what we called this was the standard matrix for the transformation. Once I know what the standard matrix is, I can use it to find other images. For example, I could say now, find T of 2, -3. And that would simply be the matrix A, which is 4, 6, 2, -7, -3, 5, times the vector x1, x2, which in this case is 2, -3. If I do that multiplication, I'll get 4 times 2 plus 6 times -3, 2 times 2 plus -7 times -3, and -6 minus 15. So I can do this transformation easily enough now, but the reason I can do it is that I've picked out the standard matrix for the transformation. Well, we can do this with general transformations, or general linear transformations as well. Let's start by remembering that the standard basis for Rn is, let's see, I want to write it this way, I guess, standard basis is equal to a collection of vectors we called E1, E2, and so on, up to E sub n. And that in Rn, what these looked like was 1, 0, 0, 0, 1, 0, and so on, all the way down to 0, 0, 1. That's the standard basis. But the standard matrix is just a matrix A whose columns correspond to each of these column matrices or vectors. So I can say that the standard matrix is 1, 0, let's see, make sure I get the right number of zeros in here. Does that look right? I think it is. And what I'm trying to convey here is that the diagonals contain ones, everything else is a zero, right? And so that's the standard matrix, but not for Rn, not for the vector space, but for the transformation T. And this is what we were calling A on the previous screen. Well, that's the way things were in 7.1, but now we're not restricted only to working with matrices that are in Rn, vectors. Our vectors may come from the polynomials, they may come from matrices, or they may come from other spaces, but in fact, we've only dealt with polynomials and matrices in this class, and that's as far as I want to take that. So because I've given you those two, and the textbook gives you those two vector spaces to draw from, in addition to the vector spaces of vectors, you've had some exposure. Just be aware that there are other vector spaces out there. So one type of vector space I can call from then, vector spaces, as far as this course is concerned, is Rn. One is P sub n, and one is matrices of M by n. And generally speaking, we're going to use, I'll just use a different color. Generally speaking here, we're going to use square matrices, and in fact, almost exclusively 2 by 2 matrices, just because that's enough for you to get the idea without it getting so overwhelming that it's not, you want to throw your hands up. So let's take a look at what a single vector, and in fact, I'm going to pick a couple of dimensions here. I'm going to say this is R, well, let's just go with R2. Let's go with P2 since we're dealing with matrices that are 2 by 2. We'll just use 2 for all of our n values. And then let's take a look at what a vector in each of these spaces looks like. I've moved some things around here a little bit. I realized I wanted to cover a fair bit of ground on this screen, and so I've moved some things around a little bit. My R2 space here so these are my vector spaces. My R2 spaces here, my polynomials of degree 2 or less are here, and my 2 by 2 matrices are over here. What does a vector in R2 look like? It is a 2-component vector we usually write as x1, x2, and that is it. And a polynomial in P sub 2 is a polynomial of degree 2 or less. I'm going to write that as a x squared plus bx plus c, where a, b, and c come from the real numbers. I don't really need to write that because, as we've said a number of times now, if I haven't specified, then we assume that the field we're working with is the real numbers. But it's always nice to be absolutely clear about it. Recall that 0 is one of the real numbers. So a, b, and or c can be 0. If A is 0, then I get, cover this up, and I've just got bx plus c. And that's no longer of degree 2, but it is of degree 2 or less, and it's because A equals 0. So a vector in this space looks something like that. A vector in the world of 2 by 2 matrices looks something like this. A, B, C, D, where A, B, C, and D come from the real numbers. I'm laughing at myself for running out of room again. Again, I didn't have to say that A, B, C, and D came from the real numbers, but it's nice to be absolutely clear. So this is what a this is what a vector looks like in the vector space 2 by 2 matrices. Now, what does a standard basis look like for x1, x2? That is a collection of vectors, each one with 2 components, so they each look like their generic model up above in the line above, but each one has a unit in one direction. So that one's got a unit in the x direction, that one's got a unit in the y direction, and then they have zeros everywhere else. I'm going to go to matrices now. I need a little bit of space here. I'm going to try to do it this way. I'm going to end up with a table. It's not really what I wanted, but that's okay. A standard basis in M sub 2 by 2 is a collection of things that look like this. And I'll go ahead and put those in there. I need 4 of them this time, because if I'm going to have a unit in each of the 4 positions that there's a number in this matrix, one here, one here, one here, one here, then I need 4. Each one has a unit in one of those positions and zeros everywhere else. So I have a 1 in column 1, 1, column 1, 2, column 2, 1, and column 2, 2, and zeros everywhere else. And that's a standard basis for 2 by 2 matrices. In the polynomials of degree 2 or less, I have, how do I say this? I'm going to put ax squared plus bx plus c. I'm going to write that down 3 times. We don't need this form. Oops, I said 3, so I was writing 3 there. It should be a 2. We don't need to write it this way, but I want to show you where it comes from. That should be squared bx plus c. Now, if each one of these has a unit in one position and then zeros everywhere else, you get this. So I'll write it up here for now, and then I'll erase this and copy it back down. So what have I got here? I've got 1x squared. I've got 1x, and I've got 1, 1. And that is the collection of vectors that makes up the standard basis for the polynomials of degree 2 or less. Now, once you have a standard basis for a vector space, you can use it to find a standard matrix for a particular transformation. In the previous video, I actually did one of these. I took a transformation, was actually 4 separate transformations, one on each of these 4 2 by 2 matrices, and I used it to sort of pick apart a single transformation and then put it back together again. And that's kind of the first step in the process. But what we're going to look at next is how to find the standard matrix, not just for, not for a vector space, but for a transformation. So you have the standard basis for a vector space, but you have the standard matrix for a transformation. Okay, I've copied our vector spaces, Rn, P sub n, and M sub, these are general, and Rn and P sub n, but I'm sticking with 2 by 2 matrices for one thing, there's 4 in this set, and it's hard enough to write 4. I'm not going to write any more than that. But for the other reason there is that I'm not going to ask you to work in this context with any matrices that are bigger than that. So then I've written down the vector spaces, and I've also written down the standard basis for each vector space. But then I've also written this down here. This is from our screen, I don't know, 2 screens ago. It feels like a long time ago. Letting the transformation T from R2 onto R3 to be defined in such a way that T, the transformation, takes a vector in X2, as it turns out, or in R2 rather, and does these things to it and spits out a vector in R3, right? Spits out a vector in R3. And what we were able to do a couple of screens ago was to use some algebra to figure out that our standard matrix, this was back in 7.1, was this. And so in each case, what we're trying to do here is that for this transformation, find this matrix. So I know a standard basis here. What I want to do is use that standard basis to find a standard matrix for each transformation that I need to do. So this matrix A does not work for all transformations from R2 to R3. It only works for this particular transformation. So we're looking for a standard matrix for a transformation. It's for a transformation, not for a space. Standard basis is a standard basis for the space. Okay, this next one is just the example in your book. Let's see. It is participation activity 7.2.3. But it's not something that you do as much as it's something that you watch. So I just kind of wanted to step through it a little bit more in detail. The transformation takes stuff in this space, 2 by 2 matrices, like this right here, that's my input, and transforms it so that it ends up in polynomials of degree 3 or less. And the way that it does that in this particular case, is this particular transformation, is it takes the value a11 from this position and makes that the coefficient of the x cubed term. a12 is the coefficient of the x squared term. a21 is the coefficient of x, and a22 is the constant. Now, a different transformation, for example, let's call it S, might take the same matrix and transform it into P3 space by making A21 the coefficient of x cubed, and A22 the coefficient of x squared, and A11 the coefficient of x, for example. That's not the transformation we're going to be working with. We're going to be working with this one. Once I've done what I'm about to do here, I will have the standard matrix for this transformation. It will not be the same as the standard matrix for this transformation. Now, the first thing to notice is that I'm taking things from 2 by the world. That should be an M, not an R. Where did I get that? I'm taking things from the world of 2 by 2 matrices, and I'm doing stuff to them, and when I do, they end up in P3. So one of the things I'm going to need to know is what is the standard basis for M sub 2 by 2, and that is over here. And what is the standard basis for P sub 3? Well, that's it here, except that this is for all polynomials of degree n, so I need to go, I need to know what my for P3, it's going to be, don't like the equals in there. My standard basis will be x cubed, x squared, x to the first power, and x to the 0 power. So I don't need anything greater than, any powers greater than 3 here. So remembering that the dimension of P sub n was n plus 1. The dimension of P sub 3 is 4, and there's four things in my collection. So those are the standard bases for the space that I'm coming from, the domain, and the space that I'm going to, the range. So now what I want to do is figure out what each of the transformations, what the transformation of each of the elements in my standard basis would be like. So what is the transformation for 1, 0, 0, 1? Right? I'm taking something that looks like this and it's going to turn it into that. But I'm going to do that, not one. I've been making so many videos, I'm getting really tired and I keep making really silly mistakes. I need to find the transformations for each of the elements in the collection that make up the standard basis. What does plugging something like this, 1, 0, 0, 0, what does that do? Well, the transformation in general takes the number in that position and makes the coefficient of the x cubed term. It scales the x cubed term by that much. And then it does the same thing to with these three values to the other terms in the polynomial. But in this case, in the case of this element of the standard basis, all three of these values are 0. So what I'm going to have is 1 times x cubed. So all this particular one does is spits out x cubed. This element from the standard basis, has a 1 in this position and zeros everywhere else. So which term has the coefficient of the A12, the first row, second column element? And that's this one here. So that's going to spit out x squared. 1 times x squared. That's going to be x squared. Then looking at the transformation of 0, 0, 1, 0, I get my 1 in row 2, column 1. And row 2, column 1 takes a sub 2, 1 takes the whatever's in this position and multiplies it by the x term. So I'm going to have 1 in this case times x. So that's just going to equal x. And I think you can see the pattern here. 0, 0, 0, 1 is just going to spit out 1. Well, another way to write x cubed is 1x cubed plus 0x squared plus 0x plus 0. Another way to write x squared, because I'm in P3 here, right? I'm in P3, that means all of my polynomials are of degree 3 or less, so I can write them as polynomials of degree 3 or less. Here I'm going to have 0x cubed plus 1x squared plus 0x plus 0, and so on. Another way to write this is 0x cubed plus 0x squared plus 1x plus 0, and finally and how we write polynomials as vectors is we take the coefficients and we write them as entries in the vector. So we have 1, 0, 0, 0. Here we have 0, 1, 0, 0. 0, 0, 1, 0. And 0, 0, 0, 1. If I put all of those together into a single matrix, I get my first column from here, my second column, my third column, and my fourth column. And that is the standard matrix for the transformation T. Now, it's a little bit different from the one in your textbook. The one in your textbook has 1s on this diagonal and 0s everywhere else. And the main reason for that is that they have also listed their terms, listed the elements in their set that are the things that make up the standard basis for P3. They've listed those in the opposite order. They've put their 1 here, their x squared here, and their x cubed as last. So they go up. The powers go up from left to right, whereas mine go down from left to right. And so this represents x cubed for me, but this position represents x cubed for the example in the textbook, just the way the textbook author has written these. One of the reasons that you sometimes see polynomials, this is just a side note. One of the reasons you sometimes see polynomials written as a plus bx plus cx squared in this order is that you can start with your constant and go until you got to your highest power. You don't have to worry about running out of room. Whereas if you start with your highest power and it turns out that there's one higher, you don't often know how far to the left you should start writing. So it's a really subtle thing here. The reason my matrix looks different from the one in the textbook is because I've written my the elements in my set in my standard basis, starting with the highest power and going down, whereas textbook authors have written with the lowest power and gone up. So that's the only difference there. I apologize for the length of this video. I know this has been a really tedious one, but I also happen to know, having been a student once myself, that you will watch what you need and disregard the rest. So I hope this has been helpful.